Hello, this is Dr. Brown. In this video, we're going to get into our logic unit, and this particular subject is going to be on proposition and truth tables. It's on page 407 to 425 in your textbook. Logic is basically the study of valid reasoning. It is a major subject in itself. I'm sure everybody in the class tries to reason carefully and use valid reasoning. Logic was developed and in order to accurately analyze statements and conclusions. When you get on Google and do searching on the internet, you're using what we call Boolean logic. Boolean logic was named after George Boole, who was a mathematician. And we use like terms like and, or. We might be looking up something like a TV, and you might say, I want a Sony or a Samsung. And you could say, but not some brand that you don't like. There are all kinds of ways to do that, but you do that to find specific web pages that fit the sets we're interested. After exploring this kind of logic, we'll look at logical arguments and how we can determine the validity of a claim. Now, a lot of the topics we're going to discuss here make what I call common sense. However, some of the notation you will need to get used to and see that the examples make sense and learn how to use the notation and work the homework. I advise you that as you go through this, at certain points, you should probably pause the video and see if you can fill in the blanks and make sure everything makes sense to you. Boolean logic. Boolean logic really combines multiple inputs or statements that are either true or false into an expression that can come out to be either true or false. For instance, using the and in Boolean logic. Suppose you wanted a sandwich that had both peanut butter and jelly in it. If this circle represents peanut butter and this represents jelly, the intersection of the circles would represent sandwiches that had both peanut butter and jelly. Now, if you didn't really care whether it was peanut butter or jelly, you just wanted one or the other, then you would be happy to get your sandwich from this set. Now, if your sandwich had to have peanut butter but not jelly, you would pick this. Now, we have what we call truth tables, and even in digital engineering, say a zero is true. I'm sorry, a zero is false, and a one is true. For, let's just take an or operation. If you have a zero and a zero, neither one of them is a one, so the output is zero. If you have a zero and a one input, they're both not one, so the output is still zero. If you have a one and a zero, you still don't have both of them being ones, so you get a zero. But the thing turns on when both are one and a one, and you get a one out. Now, if it's or, 0 and 0 gives you a 0. 0 and 1, since at least one of them is 1, you get a 1. Likewise, with 1 and 0, you get a 1, and 1 and 1, you get a 1. Now, the not operation is just the reverse. A 0 becomes a 1, and a 1 becomes a 0. For instance, this is a practical example of how you would use an AND operation in order to send an EMS to respond to something. First of all, you got to have an EMS person, and then you have to have an emergency call. If you have both those conditions at the same time, then you can send someone to respond. If you wanted to use the OR condition, you say you can prepare a meal. If you have chicken or beef, you got something to cook. Now, connection to set operations, A and B operation are elements in the intersection of A and B. A or B are elements in the union of A and B. And then not A are elements in the complement of A, which is A complement. Notice here that OR is not exclusive. This is the difference between Boolean logic and the use of common everyday English or language. When your significant other asks, do you want to go to the park or the movies, they're usually proposing an exclusive choice, one option or the other, but not both. In Boolean logic, the OR is not exclusive. So it's more like being asked at a restaurant, would you like fries or a drink with that? And you can say, yes, you'd like both. That's an acceptable answer. Okay, an example. Suppose we're searching in a library database for Mexican universities. Express a reasonable search using Boolean logic. We could start with a search Mexico and university, but would be likely to find results for the US state New Mexico because it's got Mexico in it. To account for this, we could revise our search to read Mexico and university, but not New Mexico. That would exclude any universities in New Mexico. Another example, describe the numbers that meet the condition even and less than 10 and greater than 0. Well, let's just put even numbers down and look at the condition that it's got to be greater than 0 and less than 10. So out comes 2, 4, 6, 8. And so that's these are the numbers that meet that requirement. Sometimes statements made in English can be ambiguous. That's the reason Boolean logic uses parentheses to show precedent, just like in algebraic order of operations. So let's describe the numbers that meet these conditions. Odd numbers and less than 20 and greater than 0 and multiples of 3 or multiples of 5. The first condition, odd numbers less than 20 and greater than 0, would give you 1, 3, 5, 7, 9, all the way up through 19. And then we add the condition multiples and multiples 3 or multiples of 5. So now we would need to pick out the ones that are multiples of 3 or 5, and that would be these numbers. And so out comes 3, 5, 9, and 15. All of this should be pretty straightforward and understandable so far. Statements and conditionals. A statement is either true or false. A conditional is a compound statement of the form if P then Q, or could be if P then Q else S. A statement is something that is either true or false. A statement like 3 is less than 5 is true. A statement like a rat is a fish is obviously false. A statement like X is less than 5 is true for some values of X and false for others. And this is when you would form a conditional, when an action is taken or not, depending on the value of a statement, it forms a conditional. Another example in common language, an example of a conditional statement would be, if it is raining, then we'll go to the mall. Otherwise, we'll go for a hike. The statement, if it is raining, is the condition. This may be true or false for any given day. If the condition is true, then we'll follow the first course of action and go to the mall. If it's false, then we'll use the alternative and go for a hike. Now we have the concept of quantified statements. Words that describe an entire set, such as all, every, or none, are called universal quantifiers, because that set could be considered a universal set in contrast words or phrases such as some, one, or at least one are called existential quantifiers, because they describe the existence of at least one element in a set. Quantifiers, a universal quantifier states that an entire set of things share a characteristic. An existential quantifier states that a set contains at least one element. In other words, it exists. Sometimes you need to think about negating a quantified statement. So here's some examples of coming up with the negation of various statements. So the negation of all A or B is at least one A is not B. So somebody said, suppose all A are B, and you knew that wasn't true, or if you could find at least one A that's not B, that would disprove what was said. For instance, all those in Buckhead are millionaires. I could say, well, I know a John there who is not a millionaire. The negation of no A or B is at least one A is B. So if I said nobody in my graduating class is an engineer, but then you knew that Sally is an engineer, at least one person is an engineer, then you negated that statement. I think these make pretty good sense. All you need to do is think about it. Then the negation of at least one A is B is that no A or B. An example we have at least one singer in our class. But suppose you knew that nobody in our class sings, that would negate that statement. The negation of at least one A is not B, is all A or B. Well, an example of that is at least one of my children did not have measles. If somebody knew that all of your children had measles, that would negate that statement. So you have to think about this a little bit, but I think so far it all makes common sense. Another example, somebody brought a flashlight. The negation of this is nobody brought a flashlight. Example 6, there are no prime numbers that are even. Write the negation of this statement. The negation is at least one prime number is even. Of course, that's not true for sure, because all prime numbers are odd. And but if somebody said this and you wanted to say the negation of it, it's certainly got to be that. Now we get into a little bit more notation and some more terms. Conjunction is the same as and disjunction is the same as or, and negation is the same as not. The symbol for and is this symbol. And so A and B is notated as A and B. This is, and then the symbol used for disjunction is this. And it's sort of like union. It's A or B. And then the symbol curly Q, whatever that is used for not. So something that's not A is notated as this way. So let's get a little bit into some of the notation here. We want to translate each statement here into symbolic notation. Let P represent I like Coke, and C represent I like Pepsi. P represents I like Pepsi, and C represents I like Coke. So you might want to stop for a moment and see if you can put for each of these the notation that represents these statements. I like Pepsi or I like Coke. I like Pepsi and I like Coke, etc., etc. Why don't you pause for a moment and see if you can do that on your notes. So the answer to these, I like Pepsi or I like Coke, you want to use the or symbol. So you put P or C. I like Pepsi and I like Coke, you would use the and symbol. And I do not like Pepsi, you would use a negation symbol. And this would say you don't like Pepsi. And then if you want to say it is not the case that I like Pepsi or Coke, you would put something that says I like Pepsi or Coke, and you'd put the negation of that there. And if you want to say I like Pepsi and I do not like Coke, you would use the and symbol and put Pepsi and not Coke. Now, when it comes to formally analyzing statements, they can sometimes, Boolean statements can get tricky to think about. So we probably want to create what we call a truth table to keep track of what truth values for the simple statements make the complex statement true or false. So a truth table showing what the resulting truth value of a complex statement is for all the possible truth values for the simple statements. For instance, suppose P was a statement and Q was a statement. You could have true, 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 false, false, true, and false, false as the possibilities. And then the statement that relates to P and Q would be evaluated as being either true or false. One of the simplest ones is, suppose you're picking out a new couch and your significant other says, get a sectional or something with a chaise. So this is a complex statement made of two simpler conditions. It is a sectional, which we can call S, and has a chaise. So we would use C to designate has a chaise. And notice we're looking for a sectional or something that has a chaise. So we want a truth table that looks at the statements S having a sectional and C a chaise. And we want to look at the compound statement S or C. So we put all the different possibilities, true, 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 false, false, true, false, false. And the result of this truth table, if you have both are true, obviously S or C is true. If you have a true and a false, at least one of them is true. So you get your sectional, but not the chaise. That is still true if you're satisfied with or. Now, if it has, it's not a sectional, but as a chaise, has a chaise, is true, then the output is true. But finally, if you have neither a sectional or a chaise, then the output is false. So let's look at some basic truth tables. And A and B is true only if A is true and B is true. The A union of B, or A or B, is true if A is true or if B is true or if both A and B are true. So we could create a truth table for the conjunction, which is the and operation. In other words, both have to be true in order to get an output of true. So a true, true gives you a true, true, false gives you false, false, true gives you false, false, false gives you false. However, with the disjunction, which is or, a true, true gives you true. And as long as you've got at least one true in the or function, you get a true output. False, true gives you a true, but a false, false gives you a false. Now, the truth table for negation is if the input is true, the output is false. If the input is false, the output is true. So that's the beginning of looking at truth tables. Let's show how we could create a truth table for the statement A or B. Well, we first start out with putting A and B down and the combinations of the inputs, which are 4 possible combinations. Then we add on to that table the negation of B. So we look at B, the negation of B is that's true is F, the negation of B if it's F is true, negation of true is false, the negation of false is true. So now we're still building our truth table, and next we're going to add the output that we're looking for, which is basically A or not B. So we look at A and not B. The output of that would be true. A and not B is true, true. So it's or, it's true. If we look A and not B, they're both false, so the output is false. And then finally, A is false, not B is true, then the output is true. Now we're going to introduce into this mix conditionals. A conditional is a logical statement, a logical compound statement, in which a statement P, called the antecedent, that's the first symbol in the conditional, implies a statement Q called the consequent. And I usually say consequence to tell you the truth, but really, at least in the mathematical literature, it's called consequent. A conditional is written as P, right hour Q, is translated as if P, then Q. So in other words, if P is Q, then Q is true. Consequent, if you look it up, is a thing that follows another. I say consequence myself. In fact, you might find me saying consequence in the rest of this lecture. A conditional asserts that if the antecedent is true, its consequence is also true. Any conditional with a true antecedent and a false consequence is false. So if obviously if you had a P and Q were true and true, then P then Q would be true. But if Q is false, even though P is true, then the statement if P then Q would be false. Let's talk about an example. The English statement, if it is raining, then there are clouds in the sky, is a conditional statement. It makes sense if the antecedent, which is P, it is raining, is true, then the consequent or consequence Q, there are clouds in the sky, must also be true. And it's pretty obvious if it's raining. I never have seen a rainy day which I couldn't see at least a cloud or two in the sky. Notice that the statement tells us nothing of what to expect if it's not raining. There might be clouds in the sky or there might not. However, if the antecedent is false, then the consequence becomes irrelevant. And if the antecedent P is false, then we can't figure out whether the statement is true or at least we can't prove that the statement is false. So we say that the output is true. We'll show that in just a second. In traditional logic, a conditional is considered true as long as there are no cases in which the antecedent is true and the consequent is false. Let's look at a truth table for the conditional, and then we'll explain why, if P is F, that the output is true. Well, first of all, P with a T and Q with a T leads to P, if P then Q being true. That just says it is raining and there are clouds in the sky. That is true. The second statement says it is raining and there are no clouds in the sky. That would be false, because you've never seen it raining in a condition where there are no clouds in the sky. So that is a false statement. Now, a false followed by a true, this is where the antecedent is false. It's saying it is not raining and there are no clouds in the sky. We say that it's true if we can't prove that it's false. By the same token, the second one, F, it's saying it is not raining and no clouds are in the sky. We have to say it's true if it can't be proven false. Now again, if the antecedent P is false, we cannot prove that the statement is a lie. So the result of the third and fourth rows is true. That is how we complete the table if the antecedent is false. Basically, it's like said, you are innocent until proven or proved guilty. Basically, you don't have enough evidence to prove that the statement is false. So you say it's true. Now, getting a little deeper into the notation. For any conditional, there are three related statements: the converse, the inverse, and the contrapositive. So the original condition is if P then Q, which is given by the way, this should be P then Q. There's a typo here. I'm not going to go back and change it. If P then Q, if that is true, the converse is if Q then P, notated by Q right arrow P. That may or may not be true. The inverse is if not P, then not Q, which is notated by curly P, curly Q. It also may or may not be true. But the contrapositive, we'll show this in a second. If not P, then not Q, which is notated by if not Q, then not P, it's always true. We'll show that. You have to stop and think about this a little bit. Again, consider the conditional. If it is raining, then there are clouds in the sky. It always seems reasonable to assume that it is true. In other words, if P, then Q. The converse, notated by if Q then P would be, if there are clouds in the sky, then it is raining. This is not always true. So the converse is not always true. Could be true, but may not be true depending on the statement. Now the inverse would be, if not P, then not Q. That would be saying if it is not raining, then there are not clouds in the sky. Likewise, that's not always true. There could be clouds in the sky and it still wouldn't be raining. However, the contrapositive would be, if there are not clouds in the sky, then it is not raining. That statement is true. If there are no clouds in the sky, then it couldn't be raining, and is equivalent to the original conditional. So, if P then Q is same as saying if not Q, then not P. Now, we're going to create some more truth tables here. We have already done the conditional if P then Q for inputs P and Q. So we just repeated that in this column. Now we're going to do a truth table for the converse, which is if Q then P. Just notice that if the antecedent is here and the consequent is here, this would be the result of the truth table. So now let's do the converse. We're going to do Q, if Q then P, and there we would have true first and true second. So a true gives us a true. For the next one, in which Q is F and P is true, that would be a false true, which the output would be true. For the next one, we would have a Q and a P would be a T and an F. Well, a T and an F would be an output of F. And then for the last one, we have an FF, so the Q would be F and the P would be F, and we would have an output of true. Now I'm going to erase a little bit of this. And finish the rest of the table. Well, let me erase the rest over here. Okay, for the inverse, we're going to fill out this column. for not P and not Q, for T and T, not P and not Q would be FF. And FF produces a true. For the case where P and Q are T and F, then the not P and the not Q would be FT, and an FT gives you a true. For the case in which the P and the Q were F and a T, the not P would be true, the not Q would be F, and a T and an F gives you an F. And then finally, if the input is FF for the P and Q, the input would be TT, which would be true. And then finally, let me erase a little more, show you how you get the truth table for the last one. And what I'm doing here is just using the basic truth table for a conditional. So let's do the contrapositive, which would be if not Q, then if not P. So if the input is TT, not Q would be F, not P would be F. So an FF would be true. That's why we have a T there. And then if the input was TF, then the not Q would be T, and the not P would be F, and a TF gives you an F. And then if the input for PQ was F and T, the not Q would be F, and the not P would be true. So a false true gives you a true. And finally, if the input were FF, the not P and the not Q would be true, true, and the output truth table would be true. So now, one thing to take away from this is the conditional and the contrapositive are always equivalent. And also notice that the converse and the inverse truth tables will always be equivalent. And this basically says the same thing. In other words, the original statement and the contrapositive must agree with each other. They must both be true or they must both be false. Similarly, the converse and the inverse must agree with each other, and they must both be true or they must be false. By the way, you can have all these notes to work the homework, and I know you'll need them. Here's an English example. Suppose this statement is true. If I eat this giant cookie, which is statement P, then I will feel sick, which is the statement Q. So this says if P, then Q. Which of the following statements must also be true? First statement, if I feel sick, then I ate that giant cookie. This is the converse, if Q, then P, which may or may not be true. If I feel sick, I didn't necessarily eat that giant cookie. I could be sick for other reasons. All of this is just simple logic, folks. Statement B, if I don't eat this giant cookie, then I won't feel sick. This is the inverse. If not P, then not Q. Looking at the statement, if I don't eat this giant cookie, then I won't feel sick. Again, this may not be true. I could get sick for some other reason. Statement C, if I don't feel sick, then I didn't eat that giant cookie. Now, that is the contrapositive. If not Q, then not P. This is true because if I didn't feel sick, then I must not have eaten that giant cookie, because I knew that if I ate giant cookie, I would always get sick. Notice again that the original statement and the contrapositive have the same truth value. Both are true. And the converse and the inverse have the same truth value. Both are false. Equivalence. A conditional statement and its contrapositive are logically equivalent. That's what we were just talking about. The converse and the inverse of a conditional statement are logically equivalent. Now, getting a little more into this, the negation of a conditional statement. Obviously, P, if P, then Q is a conditional statement. And one of the results of Boolean logic is that negation of a conditional statement is logically equivalent to a conjunction of the antecedent and the negation of the consequence. Basically, here's a conjunction of the antecedent, which is P. And this is, I really call this P and not Q. Now to prove that, let's go ahead and we write down the truth table for if P then Q. And then let's take the negation of that conditional, which means we negate this column. So true becomes false, false becomes true, true becomes false, and true becomes false. And now let's look at P and not Q. Well, if P is T and Q is T, then not Q would be F. So T and F, the end of that would be an F. They have to both be true. If P and not Q would be T and T, which would be true. And P and not Q would be the and of F and F, which is F. And finally, anding P and not Q would be F and T, which again would be F. So is this true? Is this column equal to this column? It sure is. We just prove mathematically this statement. Now, which of the following statements is equivalent to the negation of, if you don't grease the pan, then the food will stick to it? So let's look at these statements. The first statement is, I didn't grease the pan and the food didn't stick to it. The original statement, if you don't grease the pan, then the food will stick to it. Well, if I didn't grease the pan and I didn't get the food to stick to it, that is negation of that statement, so that's true. And in logical language, it's the conjunction of the antecedent and the negation of the consequent. To disprove that not greasing the pan will cause the food to stick, I have to not grease the pan and have the food not stick. Now, the next statement, I didn't grease the pan and the food stuck to it. Well, that's not the negation of the first statement. It's essentially the original statement with no negation. The if then has been replaced by and. Now, number C, I greased the pan and the food didn't stick to it. Basically, that agrees with the original statement, so it's not a negation. So it's pretty obvious that statement A is a negation of the original statement. The last thing we're going to be looking at here is a biconditional. A biconditional is a logical conditional statement in which the antecedent and consequence are interchangeable. And that means if P, then Q, then Q, then P is also true. A biconditional is written with double arrows pointing in right and left, and is translated as P if and only if Q. And here is the truth table. If P is true and Q is true, then P if and only if Q is true. However, if either one is false, the output is false. However, if both inputs are false, then the output is true. So a biconditional is considered true as long as the antecedent and the consequent have the same truth value. That is, they are either both true or both false. So here's how you would fill out a truth table on a biconditional. The last example, suppose this statement is true. The garbage truck comes down my street if and only if it is Thursday morning. Which of the following statements could be true? It is noon on Thursday and the garbage truck did not come down my street this morning. That cannot be true. Because if we believe the first statement, it's Thursday morning is past and the garbage truck didn't come down, but we know it always comes down no matter what. It cannot be true. It is true that I just experienced Thursday morning, but it is false that the garbage truck came because we know it always comes on Thursday morning. Statement B, it is Monday and the garbage truck isn't coming down my street. This cannot be true either. This is like the third row of the truth table. It is false that it is Thursday, but it is true that the garbage truck came because I know it always comes. Third statement, it is Wednesday, which is not Thursday, at 11:59 p.m. and the garbage truck did not come down my street today. Well, this could be true. We know it always comes down the street on Monday, but and it probably didn't come down on Thursday, but It's also false that the garbage truck came, so everything worked out like it should on Monday. Well, that's it for the logic unit. You need to think about this and go work the homework and use the truth tables to work it.